We now discuss fundamental theorem of algebra. So say you have a polynomial with coefficients in complex numbers, and this polynomial has degree greater or equal to 1. Then it has at least one root. So now using induction, you can split this polynomial completely in complex numbers. You take first root out, and then you will have some leftover polynomial. Then you apply the same theorem again to that polynomial, and then you get another root, and so on. So you can split any polynomial with coefficients in complex numbers completely over C. So before we prove this theorem, we have to keep in mind three important facts. So the first fact is that there are no finite extensions of odd degree greater than 1 of R. So that is, if you have an extension of odd degree of R, then it has to be R itself. So there are no odd degree extensions greater than 1. So let us prove this. So say you have a finite extension of odd degree. So say you have some finite extension L over R, and this is of odd degree, which is not 1. Then corresponding to this degree, you will have to have a polynomial with the same degree here. So we will have a minimal irreducible polynomial which will have an odd degree. So say this odd degree is n. We will have a polynomial also here which will have an odd degree. So first term is x to the power of n, n odd, plus some other terms. And this polynomial is irreducible. So irreducible polynomial. Now, but if you have a polynomial with odd degree, then by intermediate value theorem, this will cross the x-axis. So say if the first term is positive, you put in some high negative number, it will be below the x-axis, and then you put high positive number, it will be above the x-axis. So somewhere it will cross the x-axis, and that point would be the root. So this point right here is root n R. So by intermediate value theorem. So since it has a root in R, you already have a contradiction, because we started with saying it is irreducible polynomial over this base field R. And now by intermediate value theorem, there's a root in R. So you cannot have a finite extension of odd degree which is greater than 1. So there are no finite extensions of odd degree greater than 1 for real numbers. So the second fact we have to keep in mind is the only extension of R of degree 2 up to isomorphism is this complex numbers. So if you have a degree 2 extension of R, it is precisely the complex numbers. So corresponding to degree 2 extension, so say you construct a degree 2 extension now. Now if you have a degree 2 extension, you have to have an irreducible polynomial of degree 2 over R. And this polynomial completely splits in C by the quadratic formula. So you have any polynomial of degree 2, you use the quadratic formula, it will split in C. And if it splits in C, the uniqueness of splitting fields means that this C is iso to the other splitting field. So you have uniqueness is up to isomorphism. So again, say your degree 2 extension and the corresponding irreducible polynomial of degree 2 say looks like this. So this is our degree 2 polynomial. And then you know our quadratic formula right here gives roots like this. So you will know that these roots lie in complex numbers. So these roots lie in complex numbers. And then uniqueness of splitting fields leads to uniqueness up to isomorphism. So this is also done. So the third thing we want to show is that there are no finite extensions of complex numbers of degree 2. Now say you want to construct an extension of k over complex numbers, and this extension is of degree 2. So if you construct such an extension, now you have to associate with this degree an irreducible polynomial of degree 2. So irreducible polynomial of degree 2. So say irreducible polynomial is this, same as here, and the roots of this formula for this polynomial are again given by the quadratic formula right here. So if the coefficients are in complex numbers, so the coefficients of this polynomial, that is b and c, are in complex numbers, then this will also lie in complex numbers, because it is possible to take square roots in complex numbers. So square roots lie within complex numbers. These can be taken in complex numbers. So say if a is a complex number, the square root of a is also a complex number. So a complex implies square root of a is also complex. So notice that this is not true for real numbers, because say for example -1 is in real numbers, and you know that square root of -1 is not a real number. Similarly, 2 is a rational number, but square root of 2 is not a rational number. So this is a special property of complex numbers. But you can check this using elementary methods. So we have proven three results which we are going to use to prove the fundamental theorem of algebra. So to start with, we start with a polynomial with coefficients in real numbers. So instead of a polynomial in complex numbers, we start with the polynomial with coefficients in real numbers. And we want to show, first thing we want to show is you start with a polynomial f with coefficients in real numbers, then it splits over complex numbers. So let k be a splitting field for f. So your base field here is r, so r is here, k is the splitting field. And you cannot have an odd extension, so there are no finite extensions of odd degree, so you have to have some even extension. So this is an even extension, so you write it like this: 2m times n, where n is odd. So this is the even extension, and this is precisely the Galois group k over r. So we are talking about a splitting field, you have a irreducible polynomial, so this Galois group we represents as gf, and where n is odd. So we have done nothing, we have just constructed an extension and used this Galois group equals to the extension degree. Now let H be a CeLO2 subgroup of our Galois group. So H is a CeLO2 subgroup of GF, that is our Galois group. So CeLO2 means that order of H is 2 to the power of m. Precisely this, because order of our group is 2 to the power of m times n, so our CeLO2 subgroup has 2 to the power of m order. So the fixed field corresponding to H, say, is kh, and the Galois correspondence immediately gives that degree of extension of kh over r is this divided by h, which is n. So 2 to the power of n, so this is gf is 2 to the power of m times n, you divide it by 2 to the power of m, and you get n, which is odd. So we have this k which lies over r, we have the corresponding Galois group here, corresponding to group H you have kh right here. And to compute this degree of extension, you use the fundamental theorem of Galois theory, and you know this degree of extension is nothing but order of gf divided by h. So kh has an odd degree over real numbers, and by primitive element theorem you can say this kh is equal to r theta, and this theta lies in kh. So the minimum polynomial of theta over r has odd degree. Your degree of extension is odd, so your minimal polynomial also has to have an odd degree. Now since it has an odd degree, now you can use this result. There are no finite extensions of odd degree greater than 1 of r. So therefore it has to have root in r. So this is as odd degree, so it has to, the degree has to be 1. So if the degree is 1, it automatically has a root, so thus it is of degree equals to 1. Otherwise also you can see, you know, once you have a polynomial of odd degree over r, you can again use intermediate value theorem and say that by intermediate value theorem it has a root. So if it has a root, then obviously again this theta would lie in r, because you can solve theta over r. Or you can just see that, you know, this is odd, so degree has to be 1, because there is no finite extension of odd degree greater than 1. So kh over r is 1, so this n is 1, so kh over r is 1, so kh is equal to r, and this order of our group Galois group is precisely the order of h. So order of gf is precisely the order of h, so gf over h is 1. So since we said that h is of order 2 to the power of m, this Galois group has order 2 to the power of m, and therefore it has nested subgroups of all orders. So the orders are 2m minus k, where k lies between 0 and m. In fact, this result that the subgroups of all such orders exist, these nested subgroups exist, this is true for all prime numbers, and you can find this result on page 190 of Dummett and Foote, second edition. So here we see that now the Galois correspondence will give us fixed fields over real numbers of degree of extension 2 to the power of k. So we have our big field is k here, real numbers are here, corresponding to real numbers we have our Galois group, and you have some group here, a subgroup say h1, and corresponding field kh1. So this has order 2m minus k, this has order 2m, as we have seen before right here. So you can see the degree of extension, this degree of extension is 2m divided by 2m minus k, which is 2 to the power of k. So for k equals to 1, degree of extension is just 2. So the only extension of R of degree 2 up to isomorphism is C. So for k equals to 1, you have complex numbers, and there are no further extensions of degree 2. Now this follows from the fact that there are no further extensions of complex numbers of degree 2. So the only extension you have is for k equals to 1. So thus m equals to 0 or 1, and the splitting field for fx is R or C. So here m you can either put as 0, that is, it is just the identity map. So to start with, we had the roots already in R, or it is 1, that is degree is 2. So the splitting field is R or C. So this thing is pretty much clear. So for the first part, we start by showing that a polynomial f has coefficients lying over real numbers. Now we take it to complex numbers. So further you suppose that k over c is a finite extension of degree n. So say you have a further extension of degree n. Then k over r is 2n, because c over r is 2. So this will become 2 times n. So by primitive element theorem, k is this real numbers, adjoin alpha to it, where alpha lies in k. So the minimal polynomial of alpha will have degree 2n. So but we have already shown that polynomial over r splits in c, which is part 1. So therefore alpha is in c, and therefore k is equal to the complex numbers. So part 2 we are doing is that we are saying that suppose your polynomial lies over complex numbers, and then try to solve this result. But as you can see, there is nothing much to show here. So we have been able to prove the fundamental theorem of algebra.